little lowercase m, is talking about the mass of a planar lamina. So a planar lamina means like I have this two-dimensional region R, and I think of this as being just a weirdly shaped steel plate, like a very thin plate of metal that's practically two-dimensional because of how thin it is. It doesn't have any appreciable thickness to it, but it still weighs something,
Aluminum?
Huh?
Like aluminum?
I guess aluminum, steel, iron, whatever you want to call it. But just some very, very thin plate that still has some mass to it. Then you would calculate the mass by a double integral. You can imagine if it's round, then you could use polar coordinates, but if it's not round, then maybe you use rectangular coordinates, x and y, to do this double integral, where that rho, that's a Greek letter rho, a lowercase rho, that rho represents the density. So if you imagine it as like a steel plate, then the density is probably the same everywhere and across it because steel has relatively uniform density. But if you imagine that it's made out of different materials, like you have a plate where some patches are made out of steel and other patches are made out of aluminum, and another patch over here is made out of copper, and you've got some weird hodgepodge of melted metal, then maybe that plate would have different densities, right? Different materials, different densities. And this function rho is going to tell me what is the density of my plate at a particular point that could be given by like x and y coordinates. Okay, so that's how you calculate the mass. And then if you wanted the center of mass, this is going to be a coordinate pair with an x coordinate and a y coordinate. And the way you would calculate the x coordinate of the center of mass is 1 divided by the mass times this double integral. And what's new in this double integral is that a little x appears. And then the same thing, if you want to know the y coordinate of the center of mass, then a little y appears. And these formulas, in my opinion, are easier to remember than the Calculus 2 formulas. They're more like symmetric with respect to each other, so I don't think they're that bad. But okay. So then the next thing is these formulas for the moments of inertia. So if I write capital I with a little lowercase x, subscript there, that represents the tendency of whatever object we're talking about. In our case, we're talking about this lamina, to resist rotation about the x-axis. And so if you've got a really heavy object, but all the mass is close to the x-axis, it's actually relatively easy to rotate. That's why figure skaters hug their arms in when they want to rotate really fast. But if you've got a shape or an object where all the mass is really far away from the x-axis, then it becomes more difficult to rotate. You actually have to give it a lot more energy before it begins to rotate. And that's why if you're a figure skater and you want to slow down, then you hold your arms out and it slows you down, right? So then the same thing, if I use a subscript y, that's the tendency of the object to resist rotation about the y-axis. So the larger these values, then the more energy it takes to get them rotating. And then I don't know why this wouldn't be capital I subscript z, but I'm trying to use the same notation that your book uses, and your book uses the capital I subscript 0, so we're going to go ahead and use that. I'm sure there's a reason. But this would represent the tendency of your object to resist rotating about the z-axis. So as long as our object is completely planar lamina, meaning it only belongs to the xy plane, then these formulas are all true. With the last formula being specifically if it's an xy planar lamina. So, what's new about these formulas is that y is now squared, and that x is now squared. Also notice the difference. This is resisting rotation around the x-axis, and so we use y because y is the distance from the x-axis in the plane. And for this one, if you want the tendency to resist rotating about the y-axis, we use the x value because x is, you can think of, the x-coordinate is the distance away from the y-axis in the plane. And of course we're squaring it, so there's no negatives. And then this is kind of interesting, but if you were to take the moment of inertia with the little subscript x plus the moment of inertia with the little subscript y, then you would get these double integrals of y squared rho plus the double integral of x squared rho. But we're going to have the same variables of integration, and so antiderivatives have a property called additivity that you probably remember from Calculus 1. And additivity means that as long as I'm doing the same integral with the same variables of integration with the same bounds, I can just add these together. So it would be something like y squared rho plus x squared rho as my combined integrand. But then I would have a rho factored out, and I would have y squared plus x squared all times rho. But y squared plus x squared is r squared. And so for the moment about the, for the moment of inertia about the z-axis, I'm sure there's some good physical reason why this is the sum of the other two moments of inertia. And it turns out that the sum of those ends up giving you the double integral of r squared times your density. And you could reframe your density function in terms of probably r and theta, and then you can make the order of integration be r dr d theta with polar coordinates, and you can do it like that. Okay. So let's try to do some examples. Let's try to find the mass and the center of mass of the lamina. So I want to find m and then the two coordinates x bar, y bar. And so I'm given my rho function. So the density of this plane of this object, the density of my planar lamina, is just the x coordinate times the y coordinate. And I didn't give it to you, but this top of this region is given by y equals x squared. So for the mass, I need to set up a double integral of x times y, because that's my density function. And I'm going to allow my x values to be anywhere between, let's say, 0 and 2, and my y values to be anywhere between, actually, let me change this order of integration. And, well, actually, let me not change the order of integration, because this is a good learning moment. I'm going to let my y values be anywhere between 0 and 4. And if I let my y be anywhere between 0 and 4, then my x values have to be anywhere between square root of y and 2. Because, like here, the square root of 4 would be 2, and here the square root of 0 would be 0, and everywhere in between the square root of y, you have to just turn your head over to the side and think about how x is a function of y, and that's how you ended up getting the lower bound. If I did 0 to 4 for my y variable, and I did 0 to 2 for my x variable, that would be describing the entire rectangle, right? And so I don't want to integrate over the entire rectangle. I just want to capture this weird shape here. If I wanted to avoid this, there's another way I could write the same double integral. And so sometimes it helps to write it out 2 times. If I reverse the order of integration, now I can let my x value be anywhere between 0 and 2, And then my y value has to be somewhere between 0 and x squared to describe the same region. So either one of those integrals will give you the mass. They should give you the same answer, but then it's up to you to decide, like when you take your exam next week, you would get to decide which one you think is going to be more convenient. So I think maybe the second one could be more convenient. And taking the antiderivative with respect to y is going to give me a 1/2 xy squared, x squared and 0 dx. So that's going to be like x to the 5th dx. Then the antiderivative is going to be x to the 6th, and then of course I divide by 6, so this is 1/12 x to the 6th at 2 and 0. What is 2 to the 6th power? 64. And then 64 divided by 12. 16 thirds. Nice. So that's just the mass. That's the mass of this sheet, or the mass of this plate right here. The mass of my planar lamina is 16 thirds. And so if I want to find the center of mass, then I have to remember those formulas. So the x-coordinate is 1/m times the double integral, where I throw in a little x. And then, of course, the density function was xy, so that's really x squared y. I like the order of integration I chose, so I'm going to keep the dy dx. And that means I can keep the bounds that I was using. Maybe I should have switched pen color. And 1/m is 3/16 times integral from 0 to 2. And then I will go ahead and take the antiderivative with respect to y, which gives me x squared, y squared, and I have to divide by 2, so I'll also make that 2 times 16 out here. Evaluated at 0 and x squared dx. So I'll have 3/32 integral 0 to 2 of x to the 6th now dx. And so whenever I take that antiderivative, it's going to be 1/7 x to the 7th evaluated at 2 and 0. So what is 2 to the 7th power?
128.
Yeah, 128. And then that's going to be times 3 divided by 32 divided by 7. So 128 divided by 32 I think is 4. So 4 times 3/7, that's 12/7. That's the, again, assuming I made no mistakes, that should be the x-coordinate of my center of mass. The y-coordinate is, of course, going to be very similar. The y-coordinate is 1/m times the double integral of, this time, y times my density function, dy dx, where again x is allowed to go from 0 to 2 and y is allowed to go to 0 from x squared. And then 1/m is 3/16 integral 0 to 2. And then I've got xy squared, and I'm taking the antiderivative with respect to y, so that's going to be xy cube, and I have to divide by 3, so that's eventually going to cancel out with that 3 in the numerator. Leave it like that for right now. 0 to x squared dx. So 1 over 16 times 0 to 2 of x to the 7th dx. And of course that means, no, okay, I'm just evaluating now. I'm not taking an antiderivative yet. So that's good, right? And then that's going to become x to the 8th in there. And of course that means I have to divide by 8. So that'll be 8 times 16. So 8 times 16 is really 2 to the 3rd times 2 to the 4th. And then this is going to be 2 to the 8th. So I think the answer is 2. Yeah. Okay. And that should be the y coordinate of my center of mass. So let's see if that makes sense. And I would always advise you to check the center of mass on problems like this and just say, does that even make sense at all? And so does the coordinates 12/7 and 2 make sense? So 12/7 would be like 5/7 more than 1, which would be like right here and then right there. That would be like my center of mass. Which right now, I mean, that does not look like the center of the object. If this planar lamina had constant density, I'd be like, that's gotta be wrong. You know, the center of mass should be the point where you can like put it on your fingertip and then balance the plate, right, without it falling over. But if you put your fingertip there and you tried to balance a plate with uniform density, no, it's gonna tip this way, right? There's not as much weight over here as there is over here, so it's gonna tip over. But remember, this does not have uniform density anymore. You know, last semester where we were doing plates of uniform density, now the density is x times y. So the most density is going to occur over here where I have the greatest x times y. The density over here is 8. The density over here is 0. In fact, the density over here is 0. Right? And so as I move in this direction, the density is getting higher and higher. So I think that actually is a good answer. There's less plate above it, but there's also higher density plate. So I feel like that checks out. You're probably good.
So on the first problem, could we do just a substitution of y equals x squared and then you can do it in terms of x only?
Maybe. Try it. Try it and see if it works. Okay, well, we've only got 5 minutes, but we'll see how far we can get. It says, let R be the region in the xy plane that's bounded by the parabola y equals x squared and the line y equals x. So we're going to get a little crescent-shaped region between the origin and the point where x and y are both equal to 1. See the little bounded region there? Very skinny. And then we're going to want to calculate the mass, the center of mass, and the moments of inertia. And I don't think we're going to have time for that, but we can try. And I think you guys are pretty good at just using formulas and plugging them in by now. So maybe you already get the picture. I don't think there's any surprises. So remember, mass is going to be just the double integral over this region. And the integrand is going to be my density function, which is, again, x times y. I guess I wasn't very creative with this lecture. We got the same thing. I'll show you what it looks like to do both orders of integration. So let's try dx dy first. So my outside integral is going to be with respect to y, and so I need the bounds of integration to be constants, and I can tell that y can vary between 0 and 1, right? So 0 to 1 for my y variable. For my x variable, x has a lower bound at x equals y, right? It's the blue line is going to be my lower bound of my x variable. That's why I'm putting a y there. And then the upper bound is going to be the green curve, which is y equals x squared. But if I rearrange in terms of x, this would be y equals square root y. So it's going to go from y to square root y. That's one way you could set up that integral. And another completely equivalent way of setting up the integral is going to be the order of integration dy dx. In which case, I say that my x variable can range from 0 to 1, but then y has to have lower bound x squared and upper bound x. So either one is going to work. Let's go ahead and just do the second one. So integrating with respect to y gives me a 1/2, 0 to 1, x y squared, x dx. So 1/2, 0 to 1 of x cubed minus x to the 5th. So I've got 1/2, 1/4 x to the 4th minus 1/6 x to the 6th, 0, 1. So 1/4 minus 1/6, what is that? It would be 3/12 minus 2/12, so it would be 1/12 times 1/2 is 1/24. Oh, and that should be m, sorry. I don't know how that got turned into an x. Okay, so the mass is 1/24. We're out of time, so I'm not going to show you the center of mass or the moments of inertia. But again, you know, the centers of mass are just 1 over m times the double integral, where you pop in a little x factor for the x coordinate and a little y factor for the y coordinate, and the moments of inertia are where you use the distance from the particular axis you're talking about squared. So like for the moment of inertia on the x-axis, you're going to use y squared times your density as your integrand, and vice versa. And then you can remember that, and you can probably try this in your homework problems over the week.